Am I streaming now? Ooh, I think I maybe am. Is happening is this? Oh, right, camera. This is happening again. Hi, I'm David Connor from the White Lodge. One of my friends at the White Lodge recently informed me that just like plaid does not match stripes, Vegeta does not match khakis. So you see, if you're gonna be wearing Vegeta, you're probably gonna want something black or not khaki. Vegeta doesn't go with khakis. All right. So, anyways, as stupid as that sounds, I and actually let me just make this clear. Uh, I don't actually. I've only been looking into this problem like uh, for a couple of days now. So I've been watching like a lot of videos. And really, I've just been trying to make it through the videos. Like, in order for me to really retain this stuff and understand it, I have to, like, really pause the video every single time I come across something I don't understand. And an example of something that I don't understand is, well, let me first emphasize this. This is the fundamental problem of the Navier-Stokes Millennium Prize problem. Um, The fundamental problem is that the Navier-Stokes equations are based on the assumption that the fluid at the scale of interest is a continuum. In other words, is not made up of discrete particles, but rather a continuous substance. And so one thing that you have that makes Navier-Stokes nonlinear is the viscosity term. The viscosity term is what makes Navier-Stokes nonlinear. And so what this term, so if I open up the Millennium, an overview of the Millennium Prize problems, what this turns the Navier-Stokes problem into is a problem of logic, and not so much a problem of PDEs and fancy Nash immersions and fancy Nash embeddings and immersions. And I'll explain that in a little bit. But let me just explain. Like, this is a really good paper that covers like pretty much everything that relates to how the Euler equations, how weak solutions to Euler equations were were proved. Uh, I'm still not really stating this precisely, uh, but anyway, what I don't understand about this paper is well, let's see, yeah, just pretty much everything. So I'm really like only a couple like, but this is really a comprehensive overview of let's see, Delelis. Uh, oh, there's some videos that that if I wanted to continue working on this problem, and I kind of do because like there's a lot of very interesting approaches that have been taken to solving this problem. But it's a Delelis Institute of Advanced Study. They put out a lot of math videos that I can't understand. Um, and it's folding papers and turbulent flows. So he describes folding papers and turbulent flows. I guess they just put up the critical holder exponents. So this is something that's similar. It's along the same lines. Holder inequalities are something that's used for Navier-Stokes and in Navier-Stokes proofs. So let me just kind of emphasize here that I wish I could get to the video stream over here with the chat. All right, doesn't look like anybody's watching the thing on Navier-Stokes. All right, but anyways, so the whole thing here is that let me state my intuition. It's that, and I've got this paper printed out. Kind of reviewing it, I'm really interested in learning a little bit more about this because it covers a lot. It ties together a lot of things that I've learned a little bit about, including Nash embeddings, Riemannian manifolds, like differential equations, and just lots of things. It ties them all together and then just takes them, full speed ahead. So it's kind of like jumping into the deep end, like with sharks, and hoping that you can swim, which seems to be the approach that I kind of take for a lot of problems. And actually, that was the approach that Nash took. Like once he got his PhD with the game theory stuff, apparently he chose the algebraic geometry problem as a result of a bet with another staff member at MIT, kind of betting him that he couldn't solve it, or that just betting him to kind of challenge him on the problem of embeddings in algebraic geometry. And he actually blew people away with how he approached and eventually solved the problem because let's see. He made it. It says Nash astonished the algebraic geometry world, and proved that the only true obstructions to the existence of isometric immersions are topological. And so the solutions, like the methods that he opened the door for, became much more elegant than most mathematicians at the time expected. Um, and I mean, I kind of understand this stuff at a high level, but it's really like I know the music, I can sing along, but I don't know the notes. That really explains my level of knowledge here. However, my intuition about Navier-Stokes, a Millennium Prize problem, is that because of this, like, is my intuition is that solutions may not exist for Navier-Stokes, which seems paradoxical. You would expect that for a system of equations, if you can analytically approximate that system of equations, and your analytical approximations get closer and closer and closer to some like true solution, that there must be some numerical solution behind everything. And so the big question in Navier-Stokes is, does that does that can we prove that the numerical solution does exist, and can we prove that it is unique? Existence and uniqueness. Does a numerical solution for Navier-Stokes exist? Is that solution unique? And so in other similar problems, the solutions can be found to be unique, and generally when they are found to be unique, paradoxically, that makes it easier to identify that the solutions exist and to prove that the solutions exist. You would think it would be the other way around. It's paradoxical because you would think that, oh, you discover solutions exist, and now you discover that solutions are unique. Well, it turns out it's easier to get to you discover solutions are unique, and therefore, because they are unique, they must exist. That's not always the case, but paradoxically, it is often the case. So, uh, again, the problem here is that the term that makes Navier-Stokes nonlinear, which is what distinguishes it from the Euler equation, is the viscosity term. So the Euler equations are, it says they're quasi-linear, hyperbolic equations governing adiabatic and inviscid flow. And so I might not be getting like some of the stuff 100% correct, but as far as I know, and it does look like it's correct, there's the incompressibility condition, which is that divergence is zero across the entire fluid, which is very interesting. How do you impose the system of equations, which then you layer on top of your system of equations the imposition that divergence is zero everywhere? And that's kind of like one of the things I've been like reasoning about and thinking about. You've got this imposition that divergence is zero everywhere, which divergence is, I don't know. Anyway, so the difference between the Euler equations and the Navier-Stokes equations is that Navier-Stokes accounts for viscosity. However, it it non-localizes viscosity, and so let me explain what that means. Non-localizes, like, so since this is an ideal fluid that is a continuum instead of not being made up of discrete particles but rather a continuous substance, then viscosity, or the emulation of viscosity in the system of equations, is non-localized across the entire space, across the entire continuous like system. It's not really like viscosity is sort of like friction. It's not really like localized to the particles as they're interacting. There are no particles. And the problem here is that, to me, is the problem that makes Navier-Stokes like a proof that where the main issue is a problem of logic, is that it's all set up around faulty assumptions. Um, I don't know, and I could be completely wrong, but it seems like one of the hardest problems in it's known as one of the hardest problems in classical mechanics. It's a problem that Heisenberg worked on in his like doctoral thesis, and it was assigned to Heisenberg because his professor was kind of an asshole, but not really. But his professor like assumed that out of all the students, Heisenberg might be the only one that could make progress on Navier-Stokes, which is a problem that has existed for like I think almost 200 years. It's a really hard problem, and and really, like, again, the answer, like, the question is like, do solutions exist, and are they unique? Um, and so you can find analytical approximations to Navier-Stokes. Am I dropping frames here? I don't know. So you can find analytical approximations to Navier-Stokes. Yes, apparently I am dropping frames, but maybe not for long. What are we doing? Damn. No. 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 Is it streaming now? The hell is happening? God damn it. It says I'm live. I don't really know. I guess so. I guess I'm live. Wonderful. I'm like sitting here, looking for a red light on the camera. Am I live? Am I recording? I don't really know. You know, don't, I mean, you typically. Okay, anyways. I'm not going to make bad red light jokes. Are we good here? Because it's really fucking frustrating for me, because here's how RTMP streams work. It's a UDP protocol, and you throw packets as fast as you can. It's like not even hard. Unfortunately, they're like really easy to terminate. I'm gonna be really mad if this is inconsistent. Apparently, there's no video coming out on YouTube, and wonderful. I mean, this is great. People love having to. This is why I write blogs, because nobody's willing to like sit here and wait. Like, and I have like a ridiculously fast internet connection. I'm not getting it. I'm getting 0 dropped frames. All right. Anyways. Oh my god. It's pissing me off so much, because it just really doesn't make any sense. I mean, I guess it makes sense if there's not enough bandwidth over here. I don't I don't really need this preview thing. I just need to know. Yes, please pause that. God damn it. I'm like causing a bunch of congestion in my own network. I'm getting ready to explain something that's kind of like interesting, and I wish that people would be able to pay attention to me long enough to like not lose interest so that they can understand that I'm passionate about something that I have fucking intuition for, and then they recognize that I have some kind of like gift for math, like which is kind of undeveloped, and then they believe it's tragic that it's undeveloped, and then they actually help me instead of leaving me to fucking wallow in my own shit in poverty. But anyways, I'm like still waiting for the stream to like not like crap out. So I don't know how the stream is. I don't know. It just says it's like bad quality on YouTube, and that like I'm not getting anything, and then it's really choppy on Facebook. So, oh god, I might just record it and then send it out because this is we're stupid. I have to go watch the rest of this. Anyway, so the whole thing is that it's a bad construction. It's a proof based on a bad construction, and ideal fluids are bullshit. Ideal fluids with viscosity are bullshit, basically. And this turns Navier-Stokes into a problem that is more so a problem of logic in the proof. So, and you would think that if you construct a system of equations that it's just like any other system of equations. You have an equal sign in the middle. You have terms on the left, terms on the right. Boom, boom, boom. You know, sometimes you can have discontinuity, sometimes you can't. If you're going to have a solution in Navier-Stokes and it's going to exist for all time and be valid for all time, it can never have discontinuities, and that's important. But because it's a nonlinear thing, uh, because the viscosity term in the ideal fluid construction of Navier-Stokes introduces nonlinearity, that confounds how the system of equation behaves, and it's the Navier it is the nonlinearity that makes everything difficult because like and there have been some solutions provided for the Euler equations that use Nash embeddings to sort of uh, basically emulate this guy's approach, or I think this guy might be the guy that pioneered the approach. But basically, you take near solutions, or you start with some arbitrary value for the vector u, which represents the vector space for some particular set of solutions, and you take that, and that gives you like some kind of like Nash embedding or something that like lets you basically take the state of the system, add in the vector field, and then map that to a regular Euclidean space. So you're embedding the manifold within a larger, higher dimensional Euclidean space, and then you take that space and like kind of like crumple its parameters, kind of like folded paper, like you're kind of crunching the paper, but you're doing it slightly. So you're taking the space and you're slightly crumpling the space, and then you're kind of like you're perturbing the folding of the space, and then like gravitating towards the numerical solution. And what is counterintuitive is like this approach works for the Euler equations, but this approach does not really. It doesn't. I don't know whether or not it works for Navier-Stokes. My intuition is that it doesn't. However, if you use this approach and you gravitate towards like a more singular solution, that doesn't necessarily guarantee the uniqueness of a solution, uh, or doesn't even necessarily imply the uniqueness of a solution. Uh, Neither does it really imply the existence of a solution, but it seems like if you're like using this folding paper approach and you're kind of like getting to a more singular solution for the vector u, which represents the solution of the PDE, then it seems like if you're falling towards a more singular solution, that there would be a unique solution to the equations, or there would be the guarantee of existence to the solutions. Because you're like, if you apply this approach, given like many different like initial value sets of initial values, and given many different kinds of foldings for the like Euclidean space generated from the embedding, it seems like you would it seems like you would be approaching a more singular solution. Um, However, if solutions don't necessarily exist, you could still be gravitating towards that more singular solution without going anywhere. And so, again, my intuition is that solutions may not exist for Navier-Stokes, which seems paradoxical since if you can analytically approximate the system of equations, and those analytical approximations can become more accurate and gravitate towards like a more singular solution, not unlike the folding paper approach from Delelis, then it seems like solutions would exist. Because how can you analytically approximate some solution and be accurate when the solutions don't exist? That's what's kind of paradoxical. However, and honestly, in this and in this sense, then you have like you may have like that may like gravitating towards a more singular solution um, may indicate existence, but not necessarily uniqueness. But it doesn't even necessarily guarantee existence. Um, Further, my intuition is that if Navier Solutions has no solutions because it is a nonlinear, because it's an invalid nonlinear construction, um, from its inclusion of the viscosity term to account for friction between particles, uh, then oh well, my intuition is if Navier-Stokes has no solutions, it is because it's an invalid nonlinear construction, including from its inclusion of the viscosity term, um, and and that would just basically mean that there's no valid solutions because it's an invalid construction. However, then the challenge for the Millennium Prize becomes it becomes like dealing with the faulty logic. So you've got this construction, and you're doing everything based on the construction, which I'm calling the construction, or I'm calling the system of equations, the Navier-Stokes equations, the construction. So you've got this construction that you're using as the basis for a proof, but the construction is faulty. And so not only do you have to not only do you have to no, no, Justin, I haven't actually haven't uh, I, so not only are you like wading through like faulty construction, but you're also basing your proof around that faulty construction. So you're wading through this faulty construction. You're expecting it to either yield solutions that exist definitely, or not yield solutions that exist. And then furthermore, you're trying to ascertain whether or not those solutions are unique or not unique. And so you can't really. It's a problem of logic. You can't like you. It's very difficult to prove that an invalid construction does or does not yield results, um, or does not yield solutions. And my intuition is basically that like solutions sometimes exist. They sometimes exist, which is what is confusing. But you don't have it, like, the proof is asking for a guarantee of solutions. You don't have a guarantee of solutions. I think. I mean, obviously, I haven't worked through the proofs. I'm just saying, like, this is, like, this is my intuition, which quite often seems to be on the right track. But the point is, the point about Navier-Stokes is that you don't have guaranteed solutions, but you sometimes have solutions. So just depending on things, and like another interesting kind of thought experiment is like kind of like applying like the same motivations behind Lie algebra to the to a transition from Euler equations to Navier-Stokes equations by essentially taking this viscosity term and applying like a parameter to it that is like infinitesimal, and seeing how the system of equations reacts based on infinitesimal coefficients on the viscosity term. Where is the actual statement of this? And another thing that is so confusing about like this kind of math is that like there's always like 4 or 5 different ways to notate like equations. Okay, here it is. Well, this is basically it. That's a Cauchy momentum equation, Navier-Stokes momentum equation. It'd probably be easier for me to search for the incompressibility. Just trying to find a concise. You can find it somewhere else. Great. Seriously? Okay. Maybe we go straight to the end. But anyway, you would consider like a Lie algebra kind of approach. Like the motivation behind Lie algebra is you've got some like partial differential equation, and then you want to take some like parameter of that equation or some like component of that equation, and you want to like apply some infinitesimal transformation to it. So like if this is my like right-handed axis, you want to take it and you want to like rotate it slightly, but like infinitesimally. And so that's what I'm saying. That like that's the kind of picture that I'm trying to generate with the Navier-Stokes equations and um, the viscosity term in this equation. God damn it! I mean, you would think that there would be like Navier-Stokes momentum equation in convective form. And I think this is the. Yeah. Anyway, so you would apply it. Oh, here it is. Right? No. Kind of. You'd think there would just be one concise. Here it is. Yeah. And there's all these like subtle like variations of Navier-Stokes, because it's really like its own little world, I think, and like kind of like graduate and postgraduate research. Like there's like because people have tried to solve these things, and the whole thing to me, and it's very like caveman like, almost like like one of my favorite articles that I've written is one where I open up and I start out with by saying like this article is dedicated to Stargate, season 3, episode 22, the episode where even the simplest minds manage to identify solutions beyond the comprehension of the most advanced beings in the universe. Yes, technically it's shotgun philosophy, but it's really about intricacy, nuance, precision, and most of all serendipity. But the whole point is like this is like caveman like shotgun mathematics. Like I'm just like I mean seriously, like it seems like, uh The main problem with Navier-Stokes is assuming that it would yield solutions